Hello and welcome back. This is video number 10. Congratulations on finishing your gas laws unit, and now we're into our last unit of the year. It's going to be on acids and bases. We're not going to get too much into acids and bases today. Today's just going to be an introduction into solutions, which will eventually fit into acids and bases. So first I want you to understand what a solution is. And then how does that fit in with our unit acids and bases will be taught next lesson or next week. Okay, so this unit is going to begin as usual with a warm-up. It's just reviewing a key term that we're all, or key terms that we're all familiar with. Solutes and solvents. So I'd like you to take a second and just think about what you know about these two terms. Hopefully you could think of an example like Kool-Aid. In Kool-Aid, you have a solution, and that's what we're studying this unit, okay, at least this lesson. A solution is made up of two things, a solute and a solvent. So something is dissolved in water. So what is dissolved is the solute. What is doing the dissolving is the solvent. So solute is the sugar in Kool-Aid. The solvent is the water. So what is dissolved is the solute. What is doing the dissolving is the solvent, and it makes a solution. And today I want us to understand properties of solutions. That's what this lesson is about. So when you are done watching this video, you should have a basic understanding of solution, which includes the terms solute and solvent. You should be able to understand or imagine what a solution looks like at the atomic level. Just like the last unit, we've been imagining how gases look, even though we can't see them. I want you to imagine how solutions look at the molecular level, even though you can't see them. You can see the glass of Kool-Aid, but you can't see the molecules that make up that solution. So to understand these solutions better, I want us to be able to imagine what those molecules look like and how they're behaving when that solution is made. And how can I affect how that solution is made? How can I speed it up? What happens if I increase the temperature, the pressure, and the surface area? What happens with the properties and the dissolving process of that solution when I change those factors? And last, we're going to learn how do I describe the concentration of a solution. Okay, so this coffee is really strong, or this Kool-Aid has too much sugar. How can I describe that both qualitatively and quantitatively to communicate the strength or the concentration, how much solute there is in a solution? So that's our last goal. So this unit we're focusing on homogeneous mixtures, or the beginning of this lesson we're focusing on homogeneous mixtures, which remember are anytime you dissolve something in something and it mixes completely. So Kool-Aid, the first glass should taste the same as the next glass. That's a homogeneous mixture. Solutions fit into that category, okay, where they're evenly mixed. So we're focusing on homogeneous mixtures this lesson. And again, in these homogeneous mixtures, they have two parts, a solute, which is what is dissolved, and the solvent, what is doing the dissolving, okay? Common solvent is going to be water. Okay, and there's an infinite amount of solutes. Salt and salt water is a solute. Sugar and soda is a solute. It's dissolved in water. Carbon dioxide is dissolved in water to make soda. That's a solute. Water is going to be a common solvent. There are other solvents, but the most common one, and the one that we're going to be using this whole unit, is water. Okay, so how do I predict if I can make a solution? If I drop salt in water, will it dissolve? If I drop wax in water, will it dissolve? Well, remember, this goes back to an earlier unit. To make a solution, you can predict if it can be made using the rule like dissolves like. And this is a generalization. Nonpolar dissolves best in nonpolar, and polar and ionic dissolve best in polar. So wax is not going to make a good solution with water. It won't make a solution at all because wax is nonpolar and water is polar. But salt dissolves well in water and makes a solution because it's ionic. Remember, polar and ionic substances dissolve best in polar solutions. You can't have ionic solutions because those are solids, okay? Anyway, typically. Nonpolar solutes dissolve best in nonpolar. Polar and ionic dissolve best in polar. So this is just used to predict if I can make a solution. But how do I affect how that solution is made? How can I speed it up? How does temperature, surface area, and pressure affect the rate of making Kool-Aid? Okay, so how can, now I know how to make Kool-Aid. I put sugar and the Kool-Aid packet in water. How How do I make it faster? Well, you could heat it up. Okay, not something you typically do with Kool-Aid because you like to drink Kool-Aid cold typically. Okay, so but if you wanted to make it faster, if you had like hard chunks of sugar and it doesn't dissolve very well, okay, you could heat it up and that's going to increase that rate of dissolving, but you could also break it up. If you break up those solutes, those chunks of sugar, they're going to dissolve faster because it's going to allow a greater number of interactions between water and the individual particles. Okay, so those are the two things that are going to most affect solids. But what about gases? Gases, for example, you don't typically think about dissolving gases in solvents, but it's done all the time. Anytime you drink soda, it has gaseous CO2 dissolved in the water to make that, to give the soda its fizz. Okay, so the solubility of gases decreases with an increase in temperature. So what does that mean? If you heat up soda, okay, maybe you've drank a warm soda, I'm sure you've tried it, it's not as refreshing. Number one, because it's warm and it's not cold, and you typically drink these sodas on a hot day to cool down, but it's also more flat, so it's not going to taste as good because more of the CO2 has escaped, and you would see more bubbles leaving that soda if it's heated up. Also, anytime you open a soda, you're decreasing the pressure around it. And if you've left it out for a long time, it eventually gets flat because that gaseous soda leaves. Okay, so you've seen, or heard, anytime you open a soda, you hear that sound. That's due to the change in pressure. You're decreasing the pressure around it. If you shake it up, the soda is going to get really hard because you're increasing the pressure inside of the container. And then when I open it up, it's going to have a bigger difference in pressure and it overflows. Sometimes fizzes and makes a mess because there's a bigger difference in pressure when I open up that soda. Okay, so to summarize, solids dissolve best when heated, stirred, or ground up, and gases dissolve best when cool and the pressure is high. Okay, and we see this, here's what I was talking about earlier. When you open up a soda, you see those bubbles leave because you're decreasing the pressure. Therefore, the gas is not as dissolved. Okay, so it's escaping. Okay, all right. This is an overall chart showing how the solubility is compared to temperature. And for the most part, you see an upward trend. As temperature increases, solubility increases. But there's always going to be some exceptions here. Here we have cerium sulfate, where it's an exception. Okay, chemistry is always going to have some exceptions. But for the most part, as temperature increases, solubility increases. Okay? Especially in this unit, you don't need to worry about these exceptions, but I want to let you know there's always going to be some exceptions to any rule that I'm saying. All right, so anyway, any solution that is dissolved in water is called an aqueous solution. We've heard this before, and these aqueous solutions can be classified into two things. And these are terms you've heard, maybe not so much in my class, but you've seen. You see them all the time. If you open up your fridge, you may see these words, electrolytes and non-electrolytes, okay? On any sports drinks, you see the word electrolytes, okay? So we're going to learn what that term is and how it fits into our lesson today, solutions. Because solutions, if it's an aqueous solution, can be an electrolyte or a non-electrolyte. But what is an electrolyte? So why are they good for you? Okay, so why in sports drinks do they always advertise, this drink has lots of electrolytes? Okay, well, an electrolyte is something that can conduct an electric current. Okay, this does not mean by drinking it you're going to electrocute yourself or you're putting yourself in danger. This just means that it can carry a charge. Okay, just like you shouldn't stick a fork into a socket because it's a metal, it's like a conductor of electricity. Okay, same thing with electrolytes. Okay, I know you can't have a solid piece of Gatorade that you stick into an electrical socket. You shouldn't anyway. Okay, but it does the same thing. When it's dissolved in water, it can carry current. Okay, it can carry a charge. So technically, I guess, if you could make some wires out of electrolytes. Not very easy to do. That's why they use copper. It's a good electrolyte. But in solutions, if you have these ions dissolved in water, they are called electrolytes. And why are these good for the body? Because that's how your body is allowed to carry electrical impulses, to do things like move your fingers or think. Okay? Your body needs electrolytes to move messages throughout your body. So you need these electrolytes in your body. That's why you need, especially when you're dehydrated, to drink electrolytes. Tap water has plenty of electrolytes in it, so you get electrolytes from tap water. It's just when you're doing things that you're sweating a lot, you're losing electrolytes a lot faster. So you need to replenish them faster. Gatorade and stuff like that maybe has more electrolytes than tap water, so you're replenishing them quicker. Okay, but water does the job as well. But Gatorade is good as well. All right, so let's watch a quick video introducing this concept of an electrolyte.
We know from various lines of experimental evidence that solid sodium chloride consists of an ordered three-dimensional array of sodium and chloride ions. Solid sodium chloride is not a conductor of electricity. The ions of the ionic lattice are held in place by the strong ionic interactions in the solid and therefore are not free to move under the influence of the electric field. When sodium chloride is dissolved in water, it forms a solution of separated sodium and chloride ions. The presence of ions in the solution is responsible for the fact that the solution is a conductor of electricity. Substances such as sodium chloride that exist in aqueous solution entirely or nearly entirely as ions are called strong electrolytes. By contrast, an aqueous solution of a non-electrolyte, such as sugar, does not conduct electricity.
All right, so an electrolyte is something that can carry a charge. It doesn't provide a charge. That light was still plugged in, but when they flip the switch on, it could carry the current, okay, from point A to point B. And these electrolytes in these sports drinks and your tap water help regulate a number of your body functions. They allow your messages to be moved throughout your body, allow you to think clearly, allow you to use your muscles clearly, allows you to use your body. Okay, so salts that dissolve in water are electrolytes because when they dissolve in water, they create these ions. And this is a little different than I wanted it to be. When salt, I wanted that arrow right here, dissolves in water, it produces these two ions. Okay, so those ions are what make salt water an electrolyte. Okay, so once a compound dissolves in water, those free-flowing ions can carry the charge, allowing for the movement of electricity, making it an electrolyte. Okay, so how can we test if a substance is an electrolyte? You could use this. Again, here I have a light bulb with an open circuit. And I have one of these at school. We've seen this, I think, earlier in the year. But what I can do is I can test. Notice this light bulb is still hooked up to a battery source, so it doesn't just light up a light bulb on its own. But when it's hooked up to power and I have an open circuit, it can complete that circuit and carry the charges from point A to point B, or from the negative to the positive, okay, from the anode to the cathode. Okay, so if a solution contains electrolytes, the bulb would glow. If it doesn't contain electrolytes, it would not glow. Okay? All right. So it can move charges. All right, so now that we've defined kind of what a solution is, I want us to be able to describe how strong a solution is. Okay? And again, we're going to do that both quantitatively and qualitatively. First, we're going to learn about qualitatively. How do I describe if it's strong or weak, or what terms are we going to use? There's a couple ways you can do that. I'm sure there's more than that, but right here we're just going to learn a couple key terms: saturated and unsaturated. Okay? I use this when you describe like a towel. Okay? That towel is saturated. It's absorbed all the water it could, and it can't absorb any more. Okay? A solution is saturated when it's dissolved all of the solute it could, and it can't dissolve anymore. So if you're making Kool-Aid and you pour the sugar into Kool-Aid, if I keep pouring sugar in it forever, will it keep dissolving? No. Eventually, there's going to be some sugar start to pile up on the bottom because that solution has dissolved all of the sugar it could. It's at its saturation point, so it's reached that limit. If it's unsaturated, it hasn't reached that limit yet. Okay, for a towel, okay? A towel can absorb so much water before it's soaked, it doesn't do you any good anymore because it's saturated. It's done, it's dissolved all it could. So unsaturated, it hasn't reached that point yet. Saturated, it has. Okay? So how do I tell? Just by looking at it. An unsaturated solution looks like all the solute is dissolved. A saturated solution, you start to see this, whatever's being dissolved, pile up on the bottom. And the more salt I add, if I'm at my saturation point, the more is going to pile up because I can't dissolve anymore. Okay? I can also use a couple other terms, concentrated and dilute. Concentrated just means strong. This Kool-Aid is concentrated. It's very strong. This coffee is concentrated. It's very strong. Well, how do I make it weaker? I dilute it by adding water. Okay, so concentrated, very strong. Dilute, weak. Okay, but these are qualitative. In chemistry and in science, we want to get to quantitative. So in chemistry, we want to be as specific as possible when I'm discussing the strength of an acid or the strength of a solution. So to do that, we're going to learn 4 ways to describe the concentration of solution. And that's going to be your homework, is practicing using these 4 ways to calculate concentration. The first way, and the most common way, is molarity. So I can describe the concentration of a solution with molarity. And molarity is moles per liter. So how many moles of solute are there dissolved in a liter of solution? Typically a liter of water. Okay, so it's the ratio of moles to liters. We're going to do question number 1 on your homework, and questions number 1 through 5 are all on molarity. So here's the question. 20 grams of sodium hydroxide is dissolved in enough water to make a 1 liter solution. What is the molarity? Well, what is molarity? Remember, moles per liter. So I need to turn this 20 grams into moles. Okay, and then I dissolve by my 1 liter of solution. So how do I turn 20 grams to moles? Hopefully we haven't forgotten. Divide by the molar mass. So there's my moles. And then I take moles divided by volume in liters, remember liters, to get my molarity. And this, I describe this unit with a capital M. That means molarity, or moles per liter. Okay, that's number 1. Number 2, very similar. Okay, here I have 45 grams of glucose is dissolved in enough water to make 0.5 liters. What is the molarity? So first, why don't you pause and try to do this on your own? First, I'm going to take 45 grams and turn that to moles by dividing by the molar mass of glucose. And then I take moles divided by liters, and that gives me my molarity. Okay, again, with a capital M. So you do 3, 4, and 5 for molarity. We're going to do all these sections or examples from each. There's section 1. Section 2, another way I can describe concentration. In chemistry class, we're going to use molarity. So most of the chemicals that you would see in a chemical lab are labeled with molarity. But you don't see molarity when you go to the grocery store. Okay, if you pick up hydrogen peroxide, or if you pick up bleach or vinegar or any solution, oftentimes it's going to be percent. Okay, this is 3% hydrogen peroxide, or this is 5% vinegar. Okay, so the common population doesn't communicate concentration and molarity. I would say most people are familiar with percents. Okay, and that's probably easier for the general population. So in a chemistry lab, we use molarity. In the general public, you typically use percents. And this is a ratio. How much mass of solute is there per mass of solution? Now for this, to get mass of solution, I would write this down. Okay, 1 milliliter of water equals 1 gram. So if you have 1,000 milliliters, that equals 1,000 grams. Remembering 1 liter is 1,000 grams or 1,000 milliliters. So if you have 0.5 liters, that would be 500 milliliters. Okay, and then that would be 500 grams. Remember, there are 3 decimal places. If I'm going 2 milliliters, I move it 3 places to the right. If I'm going 2 liters, I move it 3 places to the left. Okay. For this unit, we're going to assume that every solution that I work with, every milliliter equals 1 gram. Okay. In real life, it's not always that way, but it's close, so we can simplify it. Okay. All right. So let's apply this. 20 grams of sodium hydroxide is dissolved in enough water to make a liter solution. So what is the percent composition of the solution? So I take my mass of solute, 20 grams of sodium hydroxide, over my mass of solution. So 20 grams of sodium hydroxide over my mass of the solution. Well, what is the mass of 1 liter? 1 liter, remember, is 1,000 milliliters. Every milliliter is a gram, so that's 1,000 grams. To turn it into a percent, I multiply by 100, and you get 2% sodium hydroxide. Okay, so at the store, hydrogen peroxide is typically 3%. Okay, you would have 30 grams per 1,000 grams of water to make that hydrogen peroxide. Okay, all right. So I think we're going to do one more in this section. 45 grams of acetic acid, or C6, or that would be sugar, excuse me, C6H12O6 is dissolved in water to make a 0.5 liter solution. What is the percent composition? Again, my mass of solute, 45 grams, divided by my mass of solution. The toughest part here is figuring out what this mass is. 0.5 liters is, why don't you pause and try? 500 milliliters, which is 500 grams. So 45 divided by 500 times 100 is 9% sugar. This sugar water solution. Okay. Section number 2. This is typically what you see at a grocery store. If you're reading papers, or if you have a really small concentration, the next two are more for commonly I see it with I see it with bacteria in water, okay? Or commonly, if you're studying like pollution, that's what I was looking for, pollution in rivers, okay? Hopefully there's a very small amount of pollution in rivers. If there's a really small amount of pollution in rivers, I'm going to say that's parts per million. It's the ratio of mass of solute per units of solution multiplied by 1,000,000. And typically this is used when I'm looking at, again, anytime you see things on like climate or the environment, okay? Because hopefully there's a very small amount in a large solution. Like if I take a sample of water from a lake, hopefully there's a very small amount of pollution in it, so I'm going to communicate that very small amount in parts per million. So to do that, I do the same thing, mass of solute over mass of solution, and then times 1,000,000, or times 10 to the power of 6, multiplied by 1,000,000, not by 100. So here it's the very similar problems. 20 grams divided by a liter, which again is 1,000 grams, multiplied by 1,000,000 is 20,000 parts per million. Okay? So the same thing, except instead of multiplying by 100, I'm multiplying by 1,000,000. All right. So those are very similar problems. That's section 3. One more section. Grams per liter. Good news is probably the easiest of them all. Okay? Here we just take mass of solution per volume of, mass of solute per volume of solution. Okay? You see this, I'm sure you see this maybe sometimes at the store as well. It's pretty easy to understand how much mass do I dissolve per liter of solution. Okay, so if I have 20 grams of sodium hydroxide, to make the solution, I want to dissolve it in a liter of solution. What is that grams per liter? 20 divided by 1 is 20 grams per liter. Okay, you would commonly see this, I guess, if you're following directions. Mix 20 grams in a liter of water to make this solution. Okay, but I'm sure there's other things that you can buy at the store that you'll see this concentration as well. So this, you just take grams per liter. Okay, all right. Your homework is to try to finish that worksheet. Worksheet 9.1, calculations of solution concentration. So I want you to understand how to describe quantitatively how strong a solution is. Hopefully it goes well. If you have any questions, please let me know. I look forward to seeing you this week.